In this video, we are starting our section on the fundamental theorem of line integrals. So our goals are going to be to derive what this fundamental theorem is, define what are called conservative vector fields, and solve problems involving these conservative vector fields, and overall to recognize when and how we apply this fundamental theorem of line integrals. So in this video, we will talk about what this fundamental theorem of line integrals is. So let's first recall the fundamental theorem of calculus, FTC, which says that if I have an integral from a to b of f prime of t dt, we take the antiderivative of that function, and you get f, and then you plug in that top point b minus f, plug in that bottom limit of integration a. Okay, so this relates the integral of a derivative, I have f prime of t, to just the values of the original function f at the boundary points at the a and the b. So there's a version of this for multivariable functions. So first I need to recall what's called a gradient of a function. So remember the notation for that is I write this kind of upside down triangle and then I put my function f. And the gradient is a vector where the entries are all partial derivatives. So this fx means the partial derivative of f with respect to the variable x. And similarly for this next partial with respect to y and the partial with respect to z. So let's do an example, just review how we get a gradient. For this function, if I want to write the gradient of f, we get a vector. First I take the partial with respect to x, which means I treat x as a variable, but y and z as constants. So for x squared, well, that's getting treated as a variable. This is just a normal derivative. That's going to be 2x. But then for that next term, it's just y's and z's. They get treated as constants, so that derivative is 0. So I get this plus 0. That's the partial of f with respect to x, which I could either write like this, or my other notation is I write this kind of like curvy d of f over curvy d of x. That's my other notation for partial derivatives. Now let's do the partial of this with respect to y. So now x and z are treated as constants. So x squared gets treated as a constant. That partial is 0. And then plus for the next term, y is treated as a variable, but the 3z squared is like a constant. So they will stay there, times the derivative of y is just 1. So I'll get plus 3z squared times 1. So 3z squared. Okay, comma, now we need the partial with respect to z. So x and y are treated as constants. So x squared is like a constant. That partial would be 0. Plus, for this next term, the 3y is like a constant. That gets multiplied by the derivative of z squared, which is 2z. So that'll give me 6yz. Okay, and that's my gradient. So, all right, so what does the fundamental theorem of line integrals say? If I have some smooth curve C with some initial point A and some ending point B, I'm going to draw a picture here. So imagine I have some curve. I have some curve here with some initial point A, some ending point B. I'll draw arrows for the direction of motion. Okay, so I have an initial point, some ending point, and I have a function f, lowercase f, whose gradient vector happens to be continuous on this curve. Then, when I do a line integral of my gradient vector, so that is going to be my vector field, what it ends up equaling is just the original function at the end point b minus the original function at the initial point a. So very similar to the fundamental theorem of calculus. We sort of do an antiderivative, which gets rid of the gradient, and then you plug in those endpoints. Okay, so I want to sketch out a proof for this. So, I have this curve, I'm calling the curve C, traced out here. Let's say that there's some parameterization r of t for that curve, and some interval for t for that parameterization. So at t naught, we're at this starting point. And then at t1, we're at this ending point. And let me label those coordinates. So maybe at the starting point, the coordinates are x naught, y naught, z naught. And at this ending point, the coordinates are x1, y1, z1. All right, so when I do this line integral of my gradient remember that one of the ways I can write this is I convert it to a regular integral that goes from, whatever this domain is for t, and then I take that gradient function and you dot it with the derivative of position, so dr dt, or sometimes we call that the velocity vector. Okay, so now I got to dot product the gradient with the derivative of position. So I got to multiply their components together. So the x component of the gradient, I can write that like this. I'm going to use this curvy d notation. So I'm going to use that kind of partial of f with respect to x. That'll get multiplied by the x component of the derivative of position, which is dx dt. So that's where this comes from. Plus, now I multiply the y components together, so I'll get the partial of f with respect to y from the gradient. And then, there's a typo here. Instead of a plus, this should be a multiplication. So times that y component of the derivative, dy dt. And now I do the z components. So the partial of f with respect to z times the derivative of this, dz dt. So this sum of terms that I have here involving all these derivatives, this is actually the result of a multivariable chain rule. So if you think back to earlier in multivariable calculus, you would have seen things like this before. This is actually the derivative of f with respect to t if I use chain rule. Okay, so now what I have is I have an integral of the derivative of f with respect to t, just a normal derivative. And then the integral says, well, then do the antiderivative of that derivative. So that's just our normal fundamental theorem of calculus. I will write ftc1 here. They undo each other, and you'll get the original function, f. And you got to evaluate it at those two times, t0 and t1. So at the final time, we are going to be plugging in this ending point, x1, comma y1, comma z1, or I can call that b, minus, at this initial time, I'll get f of x0, comma y0, comma z0. And that's exactly what this fundamental theorem of line integral says. In fact, this is a good time to go and highlight that formula for the fundamental theorem of line integrals. Okay, so we have a sketch of the proof. And I'm going to write a little symbol to indicate I'm done with a proof. It's a very common in math proofs to do that. So a very common symbol is I put a square and then I shade it in. Okay, so let's talk about some terminology here. So we call a vector field conservative if there exists a scalar function, lowercase f, which is going to be called a potential function where the gradient of little f equals capital F. So if that's the case, this vector field is called conservative. So the key fact is, if we're now taking a line integral along some smooth curve with some initial point and some ending point, and on top of that, if I know that my vector field happens to be the gradient of some function, lowercase f, then when I'm doing my line integral of my vector field, we'll get the line integral, and the vector field, now we're saying, happens to be the gradient of f, little f, and then I write my dot dr. Now for this, I can use that fundamental theorem of line integrals. So this will be equal to, I'll abbreviate ft, fundamental theorem, li of line integrals, which says that, okay, get the original function, lowercase f, plug in that ending point, b, minus f at the initial point, a. So in this calculation, notice that the actual path that I took from a to b didn't matter. So the actual path didn't matter. All I need to do is evaluate the original function at this ending point and at the starting point. And that can actually be really nice and helpful, especially when my path in my problem is quite complicated to work with. So one of the big questions that we will eventually try to answer in our classes, when is this going to be possible? Like, when is a vector field conservative and when is it not? So for our purposes now, just having introduced it, we are going to practice figuring out what this original function f is. So let's do an example. Let's find a potential function for this vector field f. What this means is we are trying to find a function lowercase f where the gradient of little f equals this vector field capital F. Okay, so for that to be the case, that means this x component, that should be the partial derivative of little f with respect to x. And then that y component should be the partial of f with respect to y. And this z component should be the partial of f with respect to z. So let's start to match up these things. So I need fx, the partial of f with respect to x, to be equal to 4x e to the z. Okay, so from this, let's try to figure out what the original function would look like, the original function lowercase f. So the partial derivative of that with respect to x gives me this, which means I'm now going to do an antiderivative, but just with respect to the variable x, meaning y and z are treated as constants. So for this term, x gets treated as a variable, but the e to the z gets treated as a constant. So that'll just stay there and multiply the antiderivative of 4x, which is 2x squared, and then that's still multiplied by e to the z because that gets treated as a constant. Normally when I do antiderivatives, I have my plus c, my plus the constant. But now, because I'm doing the antiderivative, just treating x as a variable, y and z are also treated as constants. So what I need to write here is I'll have a function, which I'll call c1, of y and z, which means this term could have constants, y's, and z's, because they all get treated as constants. Just as a check, if I took this function and did the partial of it with respect to x, will I get this thing? Well, for this first term, if I do the partial with respect to x, I'll get 4x e to the z. Nice. For the next term, it's just y's and z's, which are like constants. So that partial becomes 0. And then adding these together, I do get this function. So that's a good check. Okay, so now let's look at the y components. So I need fy to be equal to cosine of y. Oh, actually, let me back up one sec. Let me start with this function I have for f. And let's take the partial of this with respect to y. So for this first term, there's no y's in it, just x's and z's. Those get treated as constants. So that partial will just become 0. For this next term, there are y's in it. In fact, there's also z's. So I'm going to need to take a partial derivative of that, which I can just write as partial of c1 of y comma z over partial y. That's just how I notate that I'm doing its partial derivative with respect to y. And to match that up to this should be equal to, hopefully, should be equal to cosine of y. So, okay, I need the partial of c1 with respect to y to be equal to cosine of y. So let's do the antiderivative to try to recover what c1 of y comma z is. So I'm going to do the antiderivative with respect to y. So y is getting treated as a variable. So the antiderivative cosine of y, that's just sine of y. Okay, and then normally I'd have a plus c, but I am treating z as a constant. So not only could there be a constant, there could be z's as part of it. So I notate that by writing c2 of z. There's a function of z. To check this, let's do the partial of this with respect to y. So for the sine of y, that partial would be cosine of y. The next term has no y's, so its partial becomes 0. And then adding those together, it does equal cosine of y. Okay, so that's good. Okay, so let's highlight this a little bit. So this function c1 of y comma z, I now know it equals sine of y plus c2 of z. There's this other function of z added to it. Okay, so we are almost there. Now let's plug this back into my original function f. So let's plug it back into here. So I'll get 2x squared e to the z. Let's plug back in for that c1 to get sine of y plus c2 of z. Nice. So there's one more thing to do, which is to look at this z partial derivative. So let's take the partial of f with respect to z. So x and y are treated as constants. Z is treated as a variable. So the 2x squared is treated as a constant. That'll just stay there, multiplying the derivative of e to the z. So 2x squared just stays there, and the derivative e to the z is just itself, e to the z. Sine of y has no z's in it, so it's treated as a constant. That'll give me plus 0. And this last term does have z's in it. It only has one variable in it, z's. So that's just a normal derivative, not a partial derivative. This will be c2 prime of z. Okay, so I've done the partial of f with respect to z, but I know that should be equal to this. I know that should be equal to 2x squared e to the z. So I notice that there's a 2x squared e to the z here and here. Those can cancel. I can subtract them away. So that gives me that c2 prime of z should be equal to 0. And now I can do the antiderivative of this. There's just one variable in this, so this is a normal antiderivative. So c2 of z, what's the antiderivative of 0? That's just a constant. So I'll write just c. Okay, so I get to plug that back in for c2 of z here. So my original function f is, we got 2x squared e to the z plus sine of y. And now I know c2 of z is just a constant, so I get plus my constant. Okay, and I'd encourage you to check that if you take this and you take the partial with respect to x, you'll get this 4x e to the z. If you do the partial with respect to y, you'll get cosine of y. And if you do the partial with respect to z, you'll get this 2x squared e to the z. It's good to check that. I won't do that here in this video, but I would encourage you to do it. It's a good way to see, like, okay, does this kind of make sense? So that's my potential function. Okay, so let's do part B now, which is, given the vector field f that I was working with, find the work done along any path C that starts at this point and ends at this point. Okay, so I'm trying to find work. And remember that work is the integral over my curve of my vector field dot dr. That's how I notate this line integral. But now, based on the work we just did in part A, we can write this as a line integral of my curve over my curve. And I know that f, my vector field, is the gradient of this function little f that I just found, dot dr. And for that, I can use the fundamental theorem of line integrals. So this will be equal to, we're about to use our fundamental theorem of line integrals, which I'll just abbreviate FT, fundamental theorem Li of line integrals, which says that to get your original function little f, plug in your ending point, which is 3 pi over 2 negative 1 minus little f at the initial point, 2 pi over 2 4. So we're going to be plugging those into our function little f and subtracting. Okay, so if I plug in this first term, 2 times 9 is 18, and then I'll get e to the z, so it's e to the negative 1, plus sine of y, sine of 3 pi over 2, that's negative 1, so let me write minus 1, and then I got that plus c. Put a parentheses around that just to make it a little clearer. And then I got to subtract what I get when I plug this in for x, y, and z into my function little f. If I plug that in, I'll get 8 e to the 4 plus sine of pi over 2 is 1, and then I get plus c. If I subtract these, I'll end up with 18 e to the negative 1 minus 8 e to the 4. I'll get minus 1 minus another 1, so that's minus 2. And the c's cancel, so I just get this. Okay, nice. So in terms of actually calculating this line integral, now that I had that potential function, it was very quick. I didn't actually need my parameterization of my curve at all, just the ending point and the starting point. Of course, what made this problem still, a bit long was I did have to do this work to find the potential function, which can be tedious. But sometimes if I'm given this already, this potential function, it drastically simplifies this process of calculating this line integral. So in terms of our goals for this section, we finished the first goal, deriving a formula for that fundamental theorem of line integrals, and the second goal, defining what conservative vector fields are. We've also talked a little bit about the third goal, how do we find potential functions of conservative vector fields? But we'll continue to talk about that more in the next video.